Let's talk about something new. So here's Benjamin Franklin, and he's doing an experiment where he is flying a kite with a metal key on the string out in the middle of a thunderstorm. And that's kind of foolish, except he's doing it for science, so it's all for good fun. We're going to talk about a little bit more than that. We're talking about electricity. So if you think back when you were a kid, or when you were younger, you kind of already understand electricity a little bit. And people a very, very long time ago thought they understood electricity too. So here's our buddy Zeus. In the ancient Greeks, they understood a little bit about electricity, but really not much more than things can shock other things, or if you rub a piece of amber against cloth, then it can kind of have these magical forces where it can attract other things or repel other things. Some other ancient people, they thought that electricity kind of came from the gods. Here's our buddy Thor. He's the Norse god of thunder and the son of Odin. But it's just another example. People had an idea of electricity a long, long time ago, but they didn't really understand all the science about it. And we're going to focus most of this entire talk with is the idea of charge. Not this kind of charge. So these are the Vikings. They are charging towards the enemy. So in case you haven't seen it, there's a show on History Channel called Vikings, and it's really cool. So if you're into stuff like that, watch that. But we're going to talk about the science definition of charge. So we need to do a little bit of vocab. And we need to talk about properties of matter. You already know one, and it's called mass. And it's the amount of stuff that is in an object. And we measure that thing in kilograms. So you can have two objects of the exact same volume and size and shape and everything, and they can both have different amounts of kilograms or different amounts of mass to them. So you could have a solid concrete ball that has, let's say, 100 kilograms of mass. And you could have a beach ball of the same size, and it does not have 100 kilograms of mass. It probably has, like, I don't know, a tenth of a kilogram, something small. But the point is, there are different properties of matter, and one of the properties is mass, the amount of stuff that's there. Now, we're still going to talk about the amount of stuff, but we're a very specific amount of stuff. And this is where we get to charge. So charge is the amount of protons and electrons that are in an object. So that will define a different property of matter, and that will affect different science that we're going to talk about. So you may have already known that there are two kinds. There is positive and there is negative. Now this is just a convention that somebody decided that was, this is what everyone's going to call charge, positive and negative. The point is there's two kinds, and they have different elements to them. We could have called this red and green. We could have called this up and down. We could have called it heavy and light. We could have called it Charlie and Monica. It really doesn't matter. It's just that there's two different kinds, and they have different ways they interact with each other. So these are two charges. These are the two elementary charges, positive and negative charges. So if you have a positive and a negative, you know that they're going to attract each other. So if you had a positive particle on the left and a negative on the right, they're going to want to move towards each other. If you had two positives next to each other, they're going to go, ew, get away from me, and they're going to fly apart. If you have two negative charges next to each other, they're going to go, ew, get away from me. But then if you have a positive and a negative charge, they're going to say, you have what I lack. You are attractive to me, and I'm attracted to you. So they're going to go towards each other. So in summary, opposite charges will attract, and then like charges will repel. You probably remember this from middle school. This is not something that new, but that's the idea. Let's say we have a blob of matter, and it looks like this, and it has a bunch of positive and negative charges. And if you took the time and paused this video and counted out the number of pluses and minuses that are in here, they're going to be the same. So there's going to be the same number of positive charges as there are negative charges. So that object will become neutral. So overall, all the charges will be all canceled out. Now if you had another blob, and it had, let's say, one proton and a whole bunch of electrons, then that will become charged. So it has more charges of some kind than another. And if it's neutral, another word we can use to describe is balanced. And then if something is charged, either positive or negative, in this case it's negative because there's more negative here, we can call that unbalanced charge. So we have balanced and unbalanced charge, just like we would have balanced and unbalanced forces. So more electrons in an object means it's negatively charged. More protons in an object means it's positively charged. If there's the same amount of both, then it's neutral. Not too hard to figure all that out. So we have a very basic atom here. Now I know if you've done chemistry, you probably know there's a little bit more to what I'm telling you, but we're going to simplify it. So we have a big positive charge in the middle, and then we have an electron going around. So let's simplify it too. It has a proton in the middle, an electron on the outside, and it's spinning around. So when we talk about charges and how we would charge something or uncharge something, the things that are moving around are electrons, not the protons. So the nucleus of atoms, they don't really move around much, but the electrons are what are easily exchanged. So right now, before this electron in the bottom, let me go back a little. So right now, if you look at that atom, it is neutral. There is one positive and one negative charge. Now if I introduce a positive charge right there, that's a plus. If I not a positive. If I introduce a negative charge, then that means it's going to have one extra electron, which means it's going to be negatively charged. If I take them both away, then that means there's more positive charges than negative. In this case, there are no negative charges, so that means that one is positively charged. So we have this idea of adding or subtracting electrons. And so the elementary charge, the most basic form of charge, is just one electron, and we call that E. So you can add or lose electrons to some object, but you cannot add parts of an electron. So you can't add a third of an electron or a fourth of an electron. You can only add or subtract one electron, or add or subtract 2 electrons, or 3 electrons, and so on. So when you want to talk about the charge of something, it's going to look like this, where E is our elementary charge and N is just a number. So N could be 0, 1, 2, 3, 4, 5, all the way to infinity. And so your charge will go up by 1 electron, or down by 1 electron, or up by 2 electrons, or down by 2 electrons. It will never go up or down by parts of an electron. So it is important to know that there are discrete levels of charge that you can have. So that E actually has a number, and this E is 1.6 times 10 to the negative 19 C. This C is a Coulomb, and this is the unit of charge. So anything can have a certain number of coulombs of charge. And this is how we would measure the charge of any object. And just like the total energy, the net energy of a system is conserved, and the net energy of, or the net momentum of a system is conserved, the net charge is also conserved. Here's a piece of toast, and here's an amoeba. And let's say the toast has 2 negative charges in it, and it could give it to that blob, that amoeba over there. The total amount of charge between both objects is constant. So the total amount would just be 2 electrons, and if it stays in the system of both objects, then the total still is 2 electrons. So let's give a little bit more concrete value to this. Let's say the toast had 2 positive charges and 2 negative charges, and so did the amoeba. Now, if I moved one of my charges to the other, then it would still be the same. So let's do this mathematically so you see. So the total charge on the toast is 0, because there's 2 pluses, 2 minuses. The total charge on the amoeba is 2 pluses, 2 minuses, so it is also 0. So if you added the total charge, you get 0 plus 0 equals 0. Okay? Now let's move one of them. Let's move one of those electrons to the amoeba. Now the charge of the toast is plus 1, because there's more positive than negative. And on the right, we have one more negative. Oops, that should not be plus, that should be negative. So on the left, we have a negative charge of -1. Then, if we add all of the charges together, we get +1 plus a -1, and that would be still 0. So the total charge remains the same between the whole system. Alright, not too bad. What we're going to focus on a little bit more when we talk about charges is the forces between them. So we said that they attract or repel. We're going to talk about numerically how much. And this is how it is defined. Or actually, this is not how it's defined. This is gravity. But I'm going to use this to explain how the forces between charged objects behave. And if you notice, they look very similar. So you both have this capital G and capital K. It's actually a little k. But you have this letter in front, G and K. They're just constants. M1 and M2 are masses. Q1 and Q2 are both charges. So Q and M are both properties of matter. And then R squared is exactly the same. That's just the distance squared. So they behave in a very, very similar way. So this first equation, that's the universal law of gravitation. This is the force of gravity between any two objects. And then the bottom is Coulomb's law. This is the force between two charged particles. And they behave very similar ways. So let's break it down a little bit. So we have the force E, so F sub capital E. That's the force of charge. That is the electric force between two things. And Q1 is just the charge of one particle. Q2 is the charge of the other particle. Then R. R is the distance between the charges. And K is a constant, and it's called Coulomb's constant. Now, you don't have to memorize this, but this is what the constant actually is. It's 9 times 10 to the 9th Newton meter squared per Coulomb squared. So all of that is really not the important part here, but that's what the actual constant is. So when you have to use calculations, that's the number you use for K. Now, if we're looking at charges, there's a couple of prefixes that commonly come up all the time, because charges are often very, very small, and we don't like writing out all the decimal places, so we use the metric prefixes. One that's common is nano, and that's little n, and that means times 10 to the -9th, so it's extremely small. Another one is micro, and that is used the symbol mu that you actually use for the coefficient of friction. So sorry if that's confusing that they have the same variable that they use, but that's just how it is. So micro means 10 to the -6. So for example, something that is 10 nanocoulombs is 10 times 10 to the -9th coulombs. And something that is 10 microcoulombs is 10 times 10 to the -6 coulombs. Okay, so I'm going to break this up into 2 videos. So the first video is going to be all of the theory behind it, and from here on out to the end, they're going to be actual word problem examples. So tune in for part 2.